So again, everything you learned about differentiations and integrations of functions in the form of y equal to f of x can be carried over to vector value functions. You simply apply the rules of differentiations and integrations to individual components of the vector value functions. But certainly the definitions of the derivative or the limit definitions of derivative of vector value functions can be expressed as r prime of t is equal to the limit of r of t plus delta t minus r of t divided by delta t as delta t approaches 0, provided that the limit exists. If r prime exists, then r of t is a differentiable function. If r prime exists for all t in an open interval ab, then r of t is differentiable over the interval considerations. So more specifically, when you look at this two image, the concept of the slope of the tangent line or the slope of the secant line can be extended to the idea of vector value functions. So you have a three-dimensional space. There is a curve here written in terms of vector value functions as r of t equal to f of t, g of t, and h of t. There are two position functions, r of t, which is the initial position functions, and the ending position function is written in terms of r of t plus delta t. The terminal point of r of t is p, and the terminal point of r of t plus delta t is q. So the vector pq can be formed using a vector subtractions as r of t plus delta t minus r of t. This can also be considered as the secant vector. Okay. And if you move the point q closer and closer to p on either side of p, that is delta t approaches 0, then you can take the limit of the difference quotients here as delta t approaches 0, and you arrive at the limit definitions of derivative. And you obtain this vector right here. This is called the tangent vector. So again, as delta t approaches 0, delta r over delta t approaches r prime of t, which is a tangent vector at the point P. So if r of t is a position vector of a moving object, then r prime of t is the velocity vector of the object, which always point in the directions of motions, and the magnitude of r prime of t is the speed of the object. So here, one quick important note that we're going to have is if r of t is the position function, then r prime of t is the velocity vector of the object. The magnitude of r prime of t is the speed of the object. In a situation in which only the directions but not the length of the tangent vector is of interest, we work with the unit tangent vector, which is very important for the motions in 3D space. So the unit tangent vector is the vector with magnitude 1 formed by dividing the tangent vector by its length. So the unit tangent vector is of the form, so usually it's denoted by the capital T of t equal to r prime of t divided by the magnitude of r prime of t. So our focus in this course is not going to be in the unit tangent vector. There are two other vectors that are quite important for the motion in space. That is the unit normal vector and binormal vectors. That is for other math courses, particularly in at Bridgewater State University. The course is applied mathematics. So to differentiate a vector value function, what you do is you just take the derivative of each component of the vector value functions, and you get the results. Very similar to what we did for the case of limit of vector value functions. And that is true for the case of two-dimensional vector value function and three-dimensional vector value functions. So in example 3, we want to differentiate the following vector value function. You have the function of the form 6t plus 8i plus 4t squared plus 2t minus 3j. So again, to differentiate vector value function, we simply differentiate each of its component with respect to t. So in this case, you have r prime of t is equal to 6t plus 8 prime I plus 4t squared plus 2t minus 3 prime j. and you get the derivative of the sum is the sum of the derivative of the constant multiple. All the differentiation rules that you learned before can be directly applied here in the context of vector value functions. So derivative of 60 will give you 6, and derivative of 8 is 0, so therefore the first component is just 6i. The derivative of 4t squared plus 2t minus 3 give you 8t plus 2j, and that is the derivative of vector value functions. So when you obtain r prime, it means that is the tangent vector, or in the concept of a moving object, r prime is the velocity vector of the object. Now for part B, you take the derivative of the following functions. So r prime is equal to 3 times cosine of t prime I plus 4 times sine of t prime j. So you get negative 3 times sine of ti plus 4 times cosine of tj, and that is the answer. Or if you want to write this in the component form, you get negative 3 times sine of t, 4 times cosine of t. For part C, if you notice the last component of the functions is t times cosine of t, so that is a product. So when you take the derivative of this component, you need to apply the product rule of derivative. So r prime of t is equal to 3 prime, which is 0i, plus 4 times sine of 3t prime j plus t times cosine of t prime k hat. So for this function, the derivative of that, you need to apply chain rule. And you get, so this is 0i plus 4 times 3 times cosine of 3t j, plus, again, you need to apply product rule for this function. That is 1 times cosine of t minus t times sine of t k hat. And you can rewrite the result as 0i plus 12 times cosine of 3tj plus cosine of t minus t times sine of tk. And that is the answer. And again, you can rewrite this in terms of the component form as 0, 12 times cosine of 3t, cosine of t minus t times sine of t k hat. Next, we want to take the derivative of a vector value function of the form e to the t times sine ti plus e to the t times cosine tj minus e to the 2t times k. So the derivative of the vector value function is e to the t times sine of t prime I plus e to the t times cosine of t prime j minus e to the 2t prime k hat. So you need to apply product rule for this term, product rule for this component, and chain rule for e to the 2t. So you get e to the t times sine of t plus e to the t times cosine of t I plus e to the t times cosine of t minus e to the t times sine of t j hat minus 2 times e to the 2t k hat. And that is the answer. And for the last example, I'm just going to give you the answer because everything's going to be very similar to what we already did. So r prime of t is going to be equal to ln of t plus 1i plus 5 times e to the tj plus negative sine of t plus cosine of t k. So in the following topics, we're going to talk about the properties of derivative of vector value functions. The rule for derivative for single variable functions either carry over directly to vector value functions or have very close analogs. These rules are generally proved by working on the individual components of a vector value function. So in theorem 3, I want to mention a few rules here. So let R and U be differentiable vector value functions of t, and let little f be differentiable real value functions of t, and c be a scalar. So the first rule is the scalar multiple. That is derivative of c times r of t is going to be equal to c times derivative of r of t. For sum and difference rule, so the derivative of sum is the sum of derivative. The derivative of a difference is difference of the derivative. So if you take the derivative of vector r of t plus vector u of t, then the derivative of the sum is the sum of the derivative. In addition to that, you can do the same thing for the difference. So the derivative of the difference is difference of derivatives. Now for scalar product, that is the derivative of the real value function f of t multiplied with a vector value function u of t. So this is a product. We can directly apply the product rule of derivatives. So that is the derivative of the first function multiplied with the second plus the first function multiplied with the derivative of the second function. That is d dt of f of t times u of t plus f of t times the derivative of u of t. Now for the dot product, you have the derivative of the dot product, the derivative of r of t dot with u of t. So this is also a product. So the derivative of a product is again the derivative of the first function dot with the second plus the first function dot with the derivative of the second. So that is d dt of r of t dot with the second function u of t plus r of t dot with the derivative of u of t. For the cross product, we're going to again apply the product rule of derivative on the cross product. So the derivative of r of t crosses with u of t is equal to the derivative of r of t crosses with u of t plus r of t crosses with the derivative of u of t. Now for the chain rule, you have the derivative of the vector value functions of the form r of f of t for f again is a real value function. Then you have the derivative of the outside function evaluate at f of t multiplied with the derivative of the inside function. And we have one last rule here, that is if you have r of t dotted with itself and is equal to a constant c, then r of t dot with the tangent vector is going to be equal to 0. Therefore, the position vector is going to be orthogonal to its own tangent vector. These are the properties of the derivative of vector value function. It's very straightforward, almost directly from a single variable functions. And again, as I mentioned, this rule can be proved by working on the individual components of the vector value functions. Now we're going to do some example related to these properties. So in example 4, we want to compute the following derivatives, where you have u is equal to ti plus t squared j minus t cubed k, and v of t is equal to sine of ti plus 2 cosine of tj. Can you fix that for me, please? Plus cosine of tk. So first, I want to find the derivative of v of t squared. And this is a chain rule, so the derivative of a composite function is equal to the derivative of the outside function evaluated at t squared multiplied with the derivative of the inside function t squared. So here I got v prime t squared times 2t, so this is the regular multiplications. So the derivative of the functions v is going to be cosine of ti minus 2 times sine of tj minus sine of tk. And then when you want to find v prime of t squared, you get cosine of t squared I minus 2 times sine of t squared j minus sine of t squared k. And then you're going to substitute this into the result that we got here, and then we got the derivative of v t squared is equal to cosine of t squared I minus 2 times sine of t squared j minus sine of t squared k times 2t. So obviously, there's another way to do this calculation, is that you just basically evaluate v of t. We evaluate vt squared first and then take the derivative of vt squared that way, and then apply chain rule for each component of vt squared. However, what I did is I applied the properties of derivative of vector value function directly, so that's why this is all the step that we took. Now for part B, I want to find the derivative of t squared times v of t. So this is a product between the real value functions and the vector value function, but this is still a product rule. So derivative of the first function multiplied with the second plus the first function multiplied with the derivative of the second. So I get d dt of t squared
times v of t plus t squared times derivative of v of t. So the derivative of t squared with respect to t is 2t times v of t, which is equal to sine of ti plus 2 cosine of tj plus cosine of tk, and then plus t squared times the derivative of v of t. So the derivative of v of t we already got, which is up here. That is equal to cosine of ti minus 2 times sine of tj minus sine of tk. So it's very straightforward calculations. And now the next step is to expand everything and then combine like term. Anything related to I, you combine together. Anything related to j, you combine together. And anything related to k, you combine them together. So you get 2t times sine of ti plus 4t times cosine of tj plus 2t cosine of tk plus t squared times cosine of ti minus 2t squared times sine of tj minus t squared times sine of tk. This is equal to 2t times sine of t plus t squared times cosine of ti plus 4t times cosine of t minus 2t squared times sine of tj plus 2t times cosine of t minus t squared times sine of tk. And that's it for part B. Now for part C, we're going to find the derivative of a dot product between u and v. Of course, there are two ways to approach this problem. The first one is to take the dot product first and then find the derivative component-wise. The second approach, which we want to do in this particular context, is that we take the derivative of the dot product using the product rule of derivative. Right. So you get the derivative of the first functions, u of t, dot with the second function, plus the first function dot with the derivative of the second function. So the derivative of the first functions, right, given the first function u is equal to ti plus t squared j minus t cubed k. So therefore you get 1i plus 2tj minus 3t squared k. You dot that with v of t, which is a sine of ti plus 2 times cosine of tj plus cosine of tk. Now that's just for the first term. The second term is u of t, which is ti plus t squared j minus t cubed k, dot with the derivative of v of t, which is cosine ti minus 2 times sine of tj minus sine of tk. Now you perform this dot product. Remember, a standard unit vector dot with itself in the case of I dot with I or j dot with j or k dot with k is going to give you 1. And if I dot with j or I dot with k, they're going to give you 0 because the standard unit vector are orthogonal to one another, and orthogonal vectors are the dot product of orthogonal vector going to give you 0. So if you perform the dot product, you're going to get sine of t plus 4t times cosine of t minus 3t squared times cosine of t plus t times cosine of t minus 2t squared times sine of t and minus t cubed sine of t. And then you can combine like terms and you can arrive at the following result. That is 1 minus 2t squared plus t cubed times sine of t plus 5t minus 3t squared times cosine of t. Alright, so in this example, we look at the derivative of vector value function in using different properties. So that's it for example 4. For higher order derivative, that means if you want to take the second derivative or the third derivative or the fourth derivative or nth derivative, what you do is you just continue to take the derivative of the component of the vector value functions. Very straightforward, again, very similar to what you have learned in single variable calculus. Now, in the last topic of this lecture, I want to talk about the integrals of vector value functions. All the rules that you learned about integrals for single variable functions can directly be applied to vector value functions. And to evaluate the integral of a vector value function, you just basically integrate each component of the vector value functions. So for the definition, let f, g, and h be integrable real value functions over a closed interval a, b. You have two types of integrals, indefinite integral and definite integral. For the indefinite integral, you have the integral of r of t dt is equal to the integral of f of t dti plus the integral of g of t dtj plus the integral of h of t dtk. And to evaluate the definite integral of a vector value functions over a closed interval from a to b, I get the definite integral of r of t dt equal to the integral from a to b of f of t dt I plus the integral from a to b of g of t dt j plus the integral from a to b of h of t dt k. So now let's jump to the example. So the first example is to find the indefinite integral of vector value functions of this form. Okay, so to find the indefinite integral of these functions, you're going to basically integrate each component of the vector value functions as follow. Now you have the integral of 3t squared plus 2t dt I plus the integral of 3t minus 6 dtj plus the integral of 6 times t cubed plus 5t squared minus 4 dtk. So to evaluate this integral, you find the entire derivative of each term in the integrand. So the integral of a sum is the sum of the integral. So this should be a straightforward calculation for us at this point. So 3 times t cubed over 3 plus 2 times t squared over 2 plus c1i. Now for the second integral, you do 3 times t squared over 2 minus 6t plus c2j plus 6 times t to the 4th divided by 4 plus 5 times t cubed over 3 minus 4t plus c3 k hat. Now for c1, c2, and c3 are some arbitrary constant. Then you can simplify your result a little bit here, so you get t cubed plus t squared plus c1i plus 3 half t squared minus 60 plus c2j plus 3 half t to the 4 plus 5 over 3 t cubed minus 4t plus c3 k hat. So you can present the result of indefinite integral this way, or there's a more general form that you can produce. That is, you just write the result of the functions in terms of t's, and the arbitrary constant, you can group them together and have a vector of arbitrary constants. So that is, you have a vector of t cubed plus t squared, comma, 3 half t squared minus 60, comma, 3 half t to the 4 plus 5 third t cubed minus 4t plus an arbitrary constant vector like that, where the vector C consists of c1, c2, and c3. For the definite integral, you also integrate the vector value functions by integrating each component of the vector value functions. So here you get this equal to the integral from 0 to pi over 3 of 10 dti plus the integral from 0 to pi over 3 of sine of t dtj plus the integral from 0 to pi over 3 of e to the negative 2t dtk. So the antiderivative of 10 dt is just 10t, evaluate at 0 and pi over 3 I. So the antiderivative of psi of t is negative cosine of t, so I'm going to do minus cosine of t, evaluate at 0 pi over 3, plus, so e to the negative 2t, so there's a formula that you directly apply, or you can use u substitutions by letting u equal to negative 2t and evaluate the integral that way. But there are more direct formula that you can apply. This is going to give you negative 1/2 of e to the negative 2t, evaluate at 0 and pi over 3. Because this is the definite integral, so you don't need plus c anymore. Now you evaluate each functions as follow. You get 10 times pi over 3 minus 0i minus cosine of pi over 3 minus cosine of 0j minus 1/2 times e to the negative 2 pi over 3 minus e to the 0. So here you get 10 pi over 3 minus, so cosine of pi over 3 is 1/2 minus 1 j, so this one is I, minus 1 half e to the negative 2 pi over 3 minus 1 k hat, so I forgot the k hat here as well. Then you can quickly simplify this results, and you're going to get 10 pi over 3I plus 1 half j minus 1 half times e to the negative 2 pi over 3 minus 1 k hat. So that's it for me for this lecture. So in this lecture, we talk about calculus of vector value functions. The topics such as limit of the vector value functions, the continuity of vector value functions, the derivative and the integral of vector value function were discussed. All the rules that you learn in calculus 1 and calculus 2 can directly be applied to vector value functions. So that's it for me. Please let me know if you have any questions. Thank you.